Okay, so we're ready to get started with the first lesson, which is just what is a graph. And as I think I've maybe indicated in the intro video, we're really going to be doing proper mathematics in this course, which means that we are going to define things properly, and we're going to manipulate these objects as formal mathematicians do. Now, a graph is defined like many other objects in mathematics, like just about everything in mathematics. It's defined in terms of sets. So I want to take just a moment and go back and kind of remind ourselves what a set is and how we manipulate them, how we talk about them. So this will be about sets. And the basic thing we can do, if I give you a set S and some element X, just something, you can ask, is X in the set S or is it not in the set S? And that's really all a set does. A set is a collection of objects, a collection of things. For anything, you can ask, is it in the set S, yes or no? So if S is a set, and I give you some element X, and I'll say an element, but you should just think of this as a thing. This is just something. Then either X is in S, so we write using this special symbol, or X is not in S. And as I'm indicating here, I will read this symbol as in or not in. Now, so sets, if I give you an element, either it's in the set or not, there's really nothing more to the story. An element cannot appear in S many times. That's not possible. And there's also no additional structure to S. There's no order. So there's no first element or second element. There's nothing like that. All that happens is a set is a collection of things. For anything, either it's in your set or it's not. There's really nothing more to the story. So there's no first element, there's no ordering, there's no multiplicity. That's all there is. Now, we'll commonly use curly braces to indicate sets. So because I'm telling you that there's no ordering, for instance, if I give you this set 1, 3, 7, so a set with 3 positive integers, that's the same as the set 7, 1, 3. Those are both the set consisting of the 3 positive integers, 1 and 3 and 7. And this would also be the same. I could give you 1 and 3, 3, 7. That's still the same. Adding an extra copy of 3 doesn't matter. A set is just a collection of elements. You're in it or you're not. I'm not going to go through all of the other set notation, but I will be using it during the course of the term freely, so I'll just sort of mention a couple of the main operators we have. I think these things should be pretty familiar to you. If S and T are sets, you'd write S, we read the subset equal T, if everything that's in S is also in T. So this is S a subset. This symbol, this little upside down U without the tail, that denotes intersection. So that's if S and T are sets, this S intersect T, that's all of the elements that are common to the two sets that are in both S and T. And we as well have the union operator. S union T, this is all of the elements that are either in S or in T or in both. So as usual in mathematics, the or is the inclusive one. We allow both. So if you say like alpha or beta, you mean alpha or beta or both of them. Okay, so that's my quick blurb on sets. As I say, I'm stepping back just to put us in the right frame of mind. We are going to be doing formal mathematics. We are going to be manipulating these objects called graphs all of the time. Graphs are built from sets, so I want to just take a half step back and remind ourselves what these sets do. And now let's get to our main topic, which is graphs. Now I'm going to write down a whole bunch of definitions. I'm actually going to use the text box feature here because I can type much more cleanly than I can write with this pen. Everything that I'm writing here, it's in the lecture PDFs. So there's nothing that you really need to be recording. The point here is just to listen to my words, to put the right framework and setting in place here. So okay, so let's see how this works. Okay, so let me get my size right. That looks pretty good. Okay. So now I want to define a graph. So this is our main object for the whole term, and I'm going to sort of say this slowly and iterate it a couple of times. It's not a crazy complicated object, but there are a few parts to it. So a graph G, it's made up of two sets. So it consists of a set of vertices, and we usually denote that v of G. A set of edges, that's denoted E of G. And a relation called incidence. And the rule is that, okay, well, actually, let me just pause here for a moment. And bold a couple of these things. So I'm defining several terms here. Right. So our graph, it's made up of two different sets. So there's a set of things called vertices and a set of things called edges. And those are the two main ingredients, and they will be sets. Now there's a third thing, and this is a relation called incidence. This is a relation on the vertices cross the edges, technically. So what that means is if I give you a pair, one vertex and one edge, you can ask, are they incident or are they not? So that's what the incidence relation is. But in order to be a graph, your incidence relation has to satisfy an additional property. The rule is that every edge is incident with either one or two vertices. And these are called its ends. Okay, so again, your graph, we're gonna be thinking about these in lots of different ways. We're gonna be drawing pictures. We'll be talking about them using some descriptive language. But at the end of the day, as a formal object, a graph is a set of vertices, a set of edges, and a special relation called incidence that has the rule that every edge is incident with either one or two vertices. Okay. Right. And as I say, I'm going slowly here, and I'm saying things kind of carefully because we're trying to put these pieces into place the right way. We're going to be manipulating these as formal objects and proving theorems about them, and we need to have ourself on firm ground. Now there's one other way we're going to describe a graph. So we're sometimes going to write G equals V comma E to indicate that G is a graph with vertex set V and edge set E. You might be wondering why why do we need two different ways to say what a graph is? Is it G or is it, G equals V comma E? So why do we need two ways? And the answer here is kind of twofold. on one hand, the reality is that graph theory is an incredibly broad subject. A graph, it is fundamentally an abstract network, and these things appear in computer science and biology and physics and chemistry and every scientific discipline they're appearing, which is kind of different than what you see in, say, a lot of other areas in upper mathematics. If you're doing functional analysis, yes, it has some applications, but it's smaller. And because of that, graph theory, because it's so broad, there's no one way that everybody's accepted to do everything. So there's a lot of terminology that is specific to one area or another area of graph theory. And what I'm giving you here, these are the two usual ways that people in the subject will work with a graph. Either they take a graph and they just call it G, or they take a graph as an ordered pair of vertices and edges. There's a second reason that it's good to do this, and that's that it's just a little bit convenient for us. And I'm not going to belabor this, but when we're writing statements of theorems or we're working in proofs, it's very convenient to name only the important things that deserve to be named. Right? It's just a matter of focusing our attention on the important thing. So for instance, if I'm stating a theorem, like later in the class, we'll have a theorem that says for every graph G, omega of G is always less than or equal to chi of G. It doesn't even matter what those things are, but if I'm stating that, I don't need to tell you the vertex set of the graph or the edge set in order for that theorem to work. And so because I don't need to give those sets names, it's more convenient not to introduce them. It's just cleaner. It gets you focused on the right thing. On the other hand, at other times, we're going to say, there'll be statements, or when we're working in proofs, we're going to constantly be referencing the vertex set and the edge set, and it's just convenient to have them be a single symbol so we don't have to write lots of things every time we go to talk about them. Anyway, so that's why we're doing what we're doing. And really, this is also just getting you ready for the real graph theory literature. These are the two ways that you'll see. Okay, let me say a couple more things here. Now, incidence is a relation that relates vertices and edges. So again, for a vertex and edge, either they're incident or they're not. But there's a derived relationship called adjacency. And that's a relation on vertices, and that's also going to be super important for us. It's very easy. Two distinct vertices. Oh no, I got it right. Two distinct vertices, U and V, are adjacent if there is an edge that has those as ends. So there we are. So adjacency is a relation on the vertices of a graph, and it's a certainly really obvious and kind of natural one. If you want to focus on the vertices, there are kind of two main behaviors you see between a pair of vertices. Either there's an edge with those two as ends or not. Add one more a technical term here. So we said that when you have a graph, your incidence relation has to obey the rule that every edge is incident with either one or two vertices. And here you're welcome to start thinking about networks already. If you want to think about the vertices as nodes of a network, then if there's an edge with those two as ends, we think of there's some kind of connection between them. But we are permitting edges that have just one endpoint. And if you have just one node and that, if you have one node U and U is, if you have one node U and there's an edge E and E has only U as an end, well, then we think of that edge E as a loop. We think of it as a sort of self-connection, and we call it a loop, and we'll be drawing it like a loop. And let me just add that definition here. An edge with just one end called a loop. Another phenomena you can have is you can have two vertices, u and v, and you can have two different edges that have the same ends. They both connect u to v. And in that case, we call those two edges parallel. So two distinct edges with the same ends are parallel. And a graph without these Okay, I'm just trying to fit that on the page here. So a graph without loops or parallel edges is called a simple graph. So in many instances in graph theory, it's natural to work with simple graphs. You don't need to think about self-connections or parallel edges. In other instances, it's more natural to adopt a setting where you permit loops and parallel edges. And so by graph, I'm always going to allow the possibility of loops and parallel edges. If we say simple graph, then those things are forbidden. Okay, let's skip forward a page and talk a little bit about drawing. Now, I'm not going to write all of the words in the notes. That's not the point of this. I find it convenient to sort of type things out a little bit just to keep the rhythm here. There's a precise definition of drawing that is appearing in the notes for the class. I will just show you an example and step you through. I'll sort of say the right words here. Again, graph at a formal level, it is a set of vertices, a set of edges, and this incidence relation that tells us when vertices and edges are incident. And it has to satisfy this special rule that every edge is incident with either one or two vertices. So that's what a graph is. But how we think about it is more like a network, right? More like an abstract network. And we are going to be very quick to draw graphs because these pictures are incredibly helpful in understanding what's going on. So a drawing of a graph, it is a thing you've probably even seen before, and it is what you would think it should be. So the vertices are going to be points on the plane or on your figure. So let me draw a graph G equal V comma E. There we are. Let me give myself a little more space here. So I'm going to make a graph with about 5 vertices here. So in this case, my vertex set V is going to be the set of integers 1 on up to 5. Good. Now my edges are, my edges will have these vertices as their ends, right? So each edge is going to have either 1 or 2 of these vertices as an end. If you have an edge with 2 distinct ends, U and V, then the U and V, there are some points in your drawing, and you're going to draw that edge as a curve, a line which is allowed to be curved, connecting those 2 points. So here I'm drawing an edge with ends 1 and 2, an edge with ends 2 and 3, 1 and 3, 3 and 4. There are 2 edges with ends 3 and 4. There's 4, 5, and here's 1, 5. And there's a loop with 5 as an end. And let me label these. So I'll use letters. Here's A, B, C, D, E, F, G, H. So the edge set of my graph here is going to be the lowercase letters A on up to H. And you should readily understand from this picture which edges are incident with which vertices, right? So for instance, the edge C is going to be incident with vertices 1 and 3. D and E are parallel edges. They both have the same ends, 3 and 4. H is a loop. So H is just incident with one vertex. That's the vertex 5. So you should appreciate right off the bat that this drawing is a much more convenient way of just indicating this information about what this graph is, right? We're going to be interested in proving theorems about the structure of graphs. And when we're trying to prove something, drawing these kinds of pictures is going to be very, very helpful. It's going to get us just a picture of what's going on. So we're going to be very, very quick to draw pictures. That is where our understanding is going to come from. But very, very important, you need to understand at the end of the day, the graph, it is not the picture. The graph is just this formal object. It consists of the set of vertices, set of edges, and the incidence relation, and nothing more. So a drawing is, there are lots and lots of ways to draw the same graph. We have lots and lots of flexibility in how we draw things, but our drawings are going to be the thing we want to do to get a sense of what's going on, to tinker with this, to try to understand things. But when we go to formally write down the proof, we're going to be thinking in terms of these sets of vertices, sets of edges, and incidents. Okay, so I think that's going to be it for lesson 1. Let me stop there.